free, if you have any questions, to chat it in the chat, and I'll go ahead and address it accordingly. So I was looking over your homework before you showed up to make sure that I at least cover the questions. I cover the topic and make sure I can relate it to the homework questions to make the transition smoother. Okay. This chapter is all about chemical bonding. So at some level, we're looking at bonding from the point of view of Lewis. Now, this being a non-majors class, we look at bonding mostly from this scientist's point of view. There are many other bonding theories, but we only focus on Lewis's bonding theory. So I'm going to go ahead and start. The first thing we do is talk about the bonding that takes place between the metal and non-metal. Okay, that's the starting point. And we start off by distinguishing between cations and anions. So we'll start with that. Let me go straight to that slide. So here we're told metals lose electrons to form cations. Okay, so for the most part, when you're trying to sort out elements and you're trying to compare the different elements and place them into categories based on what is similar about them, we can take all the elements in the periodic table and categorize them or sort them into two main categories. You have the metals, you have the nonmetals, and then you have the metalloids. So the metalloids are kind of like a small categories that's kind of added in there. So the two main categories are these two, metals and the nonmetals. And the metalloids are called metalloids because they really have the properties of both metals and nonmetals. But the main categories are these two. Okay. And the metalloids tend to be in that zigzag region between the metals and the nonmetals. So let me see. Somewhere here I do have, I'm not seeing right now. I think I'll show you when we get to the periodic table. But somewhere in here I do have the periodic table that shows us. Let me scroll down here because I think I put it up earlier. The one that shows electronic configuration, because we're going to be needing that. This one right here. And I use this from my earlier class, so I still have scribbles from there. I'm telling you, almost every class I teach, I pull out the periodic table. So it's a very important part of the lesson in chemistry. Right, so let me see. I have my periodic table in front of me, and the metalloid region is the one around here. So you have this zigzag here, oops, that separates this region here that has the nonmetals. Sorry, I'm writing with my mouse, so that's kind of hard to write. I have my nonmetals right here, and then the rest of this group here, this huge group of elements right here, these are your metals. So as far as types are concerned, you can see we have a greater variety of metals than we do nonmetals, right? And then the elements that are in the border, germanium, antimony, polonium, astatine, silicon, tellurium. These right here that are in the border of both metals and nonmetals, they have both properties. And when I was trying to make sense of this chemistry stuff, trying to relate it to my life, because though people had said you can't relate it to real life, I was like, no, I will find a way to relate it to life. I realized in my travels, there weren't that many when I was younger, people who live in the border between two different areas, they tend to have a hybrid of both culture, right? Because they're so close to the border and they're being influenced by people on both sides. So it's similar in that way to the elements. The metalloids that are here tend to have the culture of both metals and non-metals. So they're able to both gain and lose electrons, as we'll see down the road. And that's how I rationalize it, by comparing the elements to people. Okay? Since I need this, let me scroll and put this down here. Y'all know I'm always trying to scroll and find stuff I need. Anyway, back to this. So our main category is metals. Metals lose electrons to form cations. Metals can lose 1, 2, or 3 electrons. So make sure you write the additional stuff I'm writing here, because remember, my goal is to expound on the information. One of the comments I've received about your second exam is terminology. Here's the thing. Chemists don't write the best. And for you to really understand the meanings of the terminology they're using, you have to read a lot to understand what they're communicating, right? Now, I try to do my best to explain what they're saying, but it does help a lot for you to read the material and understand the material, the words they're using based on context. When I was learning this years ago, I knew up front I am going to confuse cations and anions because up until the time I was learning this, I had never seen these words before and I had no reference of it. And I know my strength and my weaknesses. If I have a compare and contrast two terms, I always confuse them until I find the logic to tell one from the other. I knew one was referring to positive ions, the other one was referring to negative ions. So I'm not ashamed of my learning process. What I didn't remember the cation was I used to write my T's like this. Sometimes I still do. And the T looks like a positive. So I use the positive in here to remind me the cation that whether the cation had the letter T, T looks like a plus, therefore the cation is positive. Listen, I know, okay? It helped me get a passing grade in middle school. It helped me get a better grade in high school. It helped me get an A in college. You can see my grades improved as my technique got better, even though the content got harder. Okay? Cation definition, positively charged ions. Okay? Formed when an atom, remember, usually a metal, loses one or more electrons. And I told you how many it can lose. It can lose one, two, or three. To make things simple for you, it can lose one electron, two electrons, or three. And at you guys' level, it doesn't go beyond three. Okay? Nonmetals gain electrons to form anions. Anions are negatively charged ions. These are formed when one atom or when an atom gains one or more electrons. So let me go ahead, before we conclude with this part here, let me go ahead and detour a little bit. We'll look at some examples. So we just summarized cations. These are positively charged ions. We just learned they are made from metals. This is true, I would say, about 95% of the time. It's not always true. There are exceptions to the rules. Okay? And then what did we say? Metals lose one, two, or three electrons. By the way, I learned note writing from my not co-workers, classmates in high school. I used to really not write notes. I used to just read when I was studying. I read, and my performance in chemistry was really bad. And then in high school, when I got held back in 1 year, yes, you heard correctly, I got held back in 1 year. In my country, they do that. If you perform below standards, they hold you back. I met this group of students that was supposedly very smart, but when I started studying with them, while I was just reading and not taking notes, they were taking notes, and they summarized what they read and summarized what they understood. And so I'm like, we write all the time. They're like, yeah, well, how else will you remember? How else will you know you know? And I was like, I got it up here in my head. And they said, no, we have to write it down each time. So I'm trying to remember the methods I use, right? Anions. So even as I teach, I try to keep practicing that, which is writing down what I'm saying, right? We learned that these are negatively charged. It helps you to be accountable, and then you can visually see what you know and what you don't know, right? Negatively charged ions. Number two, made from non-metals. Number three, I said non-metals gain one, two, or three electrons. Now, I've had students in the past argue, well, the PowerPoints are already written. I'm like, yeah, but you didn't write them. And the act of writing, even though I don't know much about neurology and stuff, but the act of writing, I know my version of what's going on. It involves you more, and the more you are involved in the process, the more your brain recalls it, right? So I notice personally when I write things down, I remember it better. So I would encourage you guys to do the same thing. Even though you're watching the video, I'm the one writing, not you. So make sure you write things down so you have your own notes. Okay? And it does help you in the exam too. You have something to reference that you wrote down in your own way. Okay, I summarize this. I think it's a good time for an example. So I'm going to say here, example. Example. So I'm summarizing my notes, but as I'm doing that, I'm also illustrating a comparison, compare and contrast, right? Cations and anions are related. Remember, the cation is usually positive, the anion is negative. I have it in the notes and in words, but we see that. Let me scroll and show you, since I have the learning tool right here. This is a summary of the periodic table showing you ions based on the group number. This is going to be 1A. This is going to be 2A. Remember, we have done quantum. We've done quantum. So remember, let me draw a box around the group or the block. Remember the neighborhood block? This right here is the S block. Oh, this I should write with something darker. This is the S block. So when we talk about the A elements, make sure you know the A elements and make sure you know the S from the P, right? S block is group 1 and group 2A. P block is this whole block right here. The P block has group 3A, group 4A, 5A. Oh, I was on the roll until I realized I can't write small. Let me label this on the side. This is P block. P block. The neighborhood, P neighborhood. So I got 3A, 4A, 5A, 6A. I don't even know why this is here. 7A, 8A. You want to be aware of the Roman numbers also, okay? Okay, so where was I? Yeah, elements in group 1A. If you look at all of these elements here, what charge do they all have in common? Look at their charges, right? These elements are now being written as cations. How do I know they're cations? Look at the charges: positive, 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 positive. So these are all cations in group 1A. And then look at the trend. 2 plus, 2 plus, 2 plus, 2 plus. What is that? Group 2A. I'm going to skip over this because we usually don't predict this group right here. The D block and the F block are unpredictable. Remember this whole part here? These are D block. And then the bottom one that they didn't show right here, that's F block. These are B elements. We don't even mess with them at you guys' level so much because they're not easily predictable. So we got group 1A, we got group 2A. Then you move over here and we got group 3A. Group 3A, charge plus 3. So you see the trend. Group 1A, charge plus 1, plus 2. Then we got a plus 3 here. Okay. Group 4, it's complicated. Since I told you guys elements gain or lose up to 3 electrons, then we usually don't assign this one here charges. We skip over it. And look over here. Look at the trend. Minus 3, right? Minus 2, right? See that? Minus 1. So it's like a palindrome, right? Where the charges are plus 1, plus 2, plus 3, skip, minus 3, minus 2, minus 1, skip. So we're skipping group number 4, and we're skipping group A. Number 4, we skip number 4 because once again, elements don't usually lose 4 electrons, right? In this case here, these metals lost electrons. So I'm going to give you guys some examples and we'll go over that. And then here, these non-metals gained. Yeah, I'm running out of room. I need more room. So now that we've visualized this, I'm going to go ahead and scroll back to where I was explaining this. Okay, our example. So I'm going to pick from here in order. I'll go with sodium, magnesium. Actually, let me go vertically. Oops, no. Vertically. Let me erase that. No, come on. Okay, hold on. Sodium, magnesium, aluminum. Now assign here group number, then ion. So we can see the difference here. Okay, sodium is in group. Can you tell me what group sodium is in? I don't know if I have a periodic table somewhere here. Let me see. Let me erase all the stuff I wrote here. Can you see the position of sodium is right here? Do you know what group it is in? Well, okay, it's in period 3. Period 3 is the row. The group numbers are usually labeled up here. 1, 2, 3, 4, 5, 6, 7, 8. So we're skipping right now over group number 4, and we're skipping over group number 8 for what we're doing. Right, okay. Remember that the periodic table, I don't want to say it's a living document, but you're constantly labeling it different depending on the need. So right now, all I'm asking you is the group number, right? So for sodium being right here in group 1, then I'm going to write group 1. Okay. And then essentially, I told you the charge is based on the group number. So over here, I wrote the group numbers in red. I'm going to write the charge in black. This is going to be +1. This is going to be +2. This will be +3. So it's important to remember this trend right here. Now we have used the same periodic table and labeled it for so many different reasons, but each reason has its own labeling, right? It's a tool that is so versatile. It's used for so many different things. So now we got the group numbers in red and I have my charges in black, right? +1, +2, +3, skip over group 4, and then -3, -2, -1. I'm writing with my mouse, so excuse my horrible handwriting. Okay, so you can see there, right? Let me make this a little smaller, but hopefully you can still see. Based on that, what's the group number for sodium? Oh, sorry, I already answered that, right? 1. What's the charge on sodium based on its group number? +1, right? So you're going to write sodium +1, but the +1 part is implied, so you just write it as positive, okay? Don't leave it as just Na, you have to write positive, okay? Very good. Next one, magnesium, its neighbor right here next to it. What can we say about magnesium? What's the group number for magnesium? Once again, you're reading vertically for the group number, right? So 2, right? Very good. What's the charge on magnesium? Or the name of the ion symbol? Very good. So Mg +2. So it's important to know, as I was reading over your homework, it's important to know, it's hard for me sometimes to think like a non-majors person because I've been in chemistry too long to think that way. That's why I really rely on you guys to ask me questions because it helps to recalibrate my mind. But yeah, when they ask for the ion, or they can ask for the symbol of the ion, they want you to write the name, and I mean the symbol and the charge. When they ask you for the charge alone, then you put like positive or whatever, okay? So we move over to aluminum. Aluminum is in group 3. Its charge is +3, but the symbol of the ion, or the ion symbol, is Al3+. Okay, so it's important to make sure you understand the symbol or you will pick the wrong answer. Okay, so that's it for that part. Now for this part, usually I gave you the example without looking over there, but let me try to mix it up a little bit. I'll say oops, no, not that. I'll say nitrogen, sulfur, iodine, NSI. Okay, that's my element. We'll look at group number like before, and we'll look at ion. Just like before, you look at nitrogen right here. It's in group 5, right? And then the charge is -3. So they're asking you not for the charge here, they're asking for the ion. So it should be N -3. Here's the other way of getting the charge for this one here is you take the group number -8. So 5 minus 8 gives you -3. For me, that's too much work. I just go +1 +2 +3 -3 -2 -1. It's a palindrome. The number gets bigger, you skip, and then it gets smaller, and then the signs are opposite. That's how I remember it. Okay, sulfur. Sulfur is right here. So nitrogen, sulfur. Sulfur is in group 6. You can see that up here, group 6. Iodine is in group 7. Sulfur has a charge of -2 right here. So S -2. Iodine has a charge of -1. I -1, where the 1 is implied. So we leave it as is. Okay? So by me using this, I've just shown you examples of cations and anions. And here they are. Remember, you can use the group position to figure out what they are if they are monoatomic, made up of a single element. Okay? So I kind of went over a lot. When we are done, when we have our cations, remember these are positive, and anions negative, once they are made, they have opposite charges. These are opposite charges. They will then attract to form ionic bond. So once these are formed, they can combine, the cations can combine with anions to form ionic bonds. And this is called ionic bonds because ions were formed first before the bond was formed. Okay? Cations and anions bond to form ionic compounds. So it's important to pay attention to the details so you can understand what is being asked when you're working with a problem. Okay? Any questions about this? Okay, so we are moving on. Now here, which I'm trying to check off the things we're going over that pertain to your homework. We identified anion bonds. Let's see, ionic versus, yeah, I have the ionic versus anionic versus cationic. We've done with that. The next one is electronic configurations. We're about to do that. This is in your homework, so I'm covering it right now. In your homework, there's a question asking you about isoelectronic. Okay, let me start with isoelectronic and I'll go through a bunch of these. Isoelectronic, this is a term you need to know. So I'll say here, no. I mean, I won't say no. I'm saying it, know it, and I'm highlighting it. You need to know this. Iso means same. Electronic is referring to electronic configuration and number of electrons. So let's examine that before we look at the actual electronic configuration. Let's look at situations where we have same electrons, okay? So isoelectronic, same number of electrons. So before we get into the configuration, let's deal with this concept at this basic level, and then we'll go deeper. Okay, so I am going to copy, let me use this so you guys can see what I'm looking at. Okay, I'm gonna erase this now. Wait, I thought I was erasing. Okay, I'm gonna erase this now. I'm using my periodic table, but I'm using it for different reasons. So how about this? I am look at sodium. And here's my charge. Make the following isoelectronic. Now, you don't have any homework question that asks you this, but I'm making up a question, and as we're answering it, we're learning the concept of isoelectronics. So I'm going to make the formulas that I'm going to give myself have the same number of electrons. How do I do that? Let me select a series of electrons or elements. I'll say sulfur, chlorine, argon, potassium, calcium. So let me actually say isoelectronic with argon. And I'll remove this from here. Okay. Can I add one more to make this interesting? I'll say phosphorus. Okay. Make the following isoelectronic with argon. So let me load it so you can see my question. Make the following isoelectronic with argon. Can I move this up? Maybe I can. Let me see. Oh yeah. So here's the deal. I have to make the following formulas here have the same number of electrons as argon. Okay, so to do that, let me figure out, first of all, how many electrons does argon have? Oh, did I do something? Did I hide it? Oh, there it is. Okay, argon has 18 electrons. So this has 18 electrons. Let me see how many sulfur has. Sulfur has 16, chlorine has 17, phosphorus has 15, potassium has 19, and calcium has 20. Okay, I wrote this all. Okay. Phosphorus has 15, potassium has 19, calcium has 20. Okay, but we have to make all of these end up with 18. I'll start with my first one. Since sulfur only has 16, do we need to remove 2 electrons or add 2 electrons? Okay, so I'm going to add 2 electrons. Then we end up with 18. But in the process, because sulfur has to gain 2 electrons, it becomes 2, I'll say negative 2. The charge on sulfur now becomes negative 2. Why? Because I added 2 electrons to sulfur to make it isoelectronic with argon. Okay. What about chlorine? What do I do? Do I remove electrons or add electrons? Okay. And I'm adding 1, right? So I'm going to add 1. Think about this kind of like a game. Sulfur started off in this position right here, having only 16 electrons. We're trying to get sulfur to be like argon, isoelectronic with argon. So it has to move 2 spots, and to do that, it has to gain 2 electrons without changing the element sulfur. So sulfur goes from here, gains 2 electrons, moves 2 spots, 1, 2. When sulfur is here, to have 18 electrons, we have to label it as -2, meaning it gained 2 electrons, right? So I'll change the language here and say, because the language they'll give you is gains 2 electrons to become this. Here, gains 1 electron to become Cl minus. Also now having 8 electrons. Let's see, phosphorus. Phosphorus being here at 15, we can tell it has to gain to move forward, right? And you can see it has to gain 3 electrons to move, forward. 3 steps. So when it gains 3 electrons, it now has 18 electrons, but the symbol has changed to -3 because it gained 3 electrons to be at this position right here. Potassium has passed argon, but we want it to go back to where argon is. So what does potassium have to do? Does it have to gain or lose? It has to lose, exactly. Potassium loses 1 electron. and then it becomes K plus. Now it has 18 electrons when it's K plus, right? And you can see calcium would have to lose 2 electrons to move 2 spots back here. So calcium lose 2 electrons and becomes Ca2, 2 plus, so plus 2. Let me be consistent. 18 electrons. And if I had wanted to, I could include, this one would be a little bit complicated because this one has got more electrons than that. If this one loses a couple of electrons, it just moves back to the spot, right? Anyway, the ones that we have are like this. So you can see these two are metals based on where they are located, right here and here. So they become cations by losing electrons, the same concept again. And then the nonmetals, these three, become anions by gaining electrons. They gain electrons though. Look at what happens to them. For all of these, as metals and non-metals gain, I should say lose or gain, because the metals lose first, lose or gain electrons, comma, they become isoelectronic as group 8 elements. So down the road, we'll learn about octet rule. In the octet rule is explaining the behavior of metals and nonmetals, which is saying that metals will either gain, nonmetals will lose. Sorry, metals will lose, nonmetals will gain electrons, or nonmetals will share electrons to become isoelectronic with group 8 elements, and they call that the octet rule. Okay, so down the road, we'll talk about this in the context of bond formation. So now that we see that, in this table here, they explain a lot to you, starting with what's happened with nitrogen. So nitrogen from the group that we saw right here starts off with 7 electrons. So this Z here is just saying Z's atomic number. Nitrogen has 7 electrons. Its group number is 5A. They're showing you here nitrogen has 7 protons and 7 electrons based on its atomic number. Okay? They're showing you the Lewis dot structure, which I think we learned this before, but we are learning it over again. So quick recall. The group number, now I can't even spell. Let me write it out so I can write it out properly in detail. Because this table holds a lot of information, which is atomic number equal number of protons. Number 1. Number 2, in a neutral atom, this means there's no charge, number of protons equal number of electrons. Okay? That's why when you look at up there, you had atomic number equal number of protons, which we learned this before, equal number of electrons. We also learned this before, so it's kind of a summary of a lot of things. Group number equal number of electron dots. Okay? If you look at the group number, it matches the number of electron dots. Trying to see what else we have right here. Okay. So as we're going over this right here, I've summarized some of the main things we're going to be looking at. So starting with nitrogen. Nitrogen, they tell you the atomic number, they tell you the number of protons, number of electrons. And they're about to tell you what transformation we see. They're showing you here, based on the group number, nitrogen actually gains 3 electrons. I already showed you guys all that stuff, right? Only I showed you from a different point of view. Nitrogen being in group 5 will gain 3 electrons to move 3 spots to group 8. And doing that, the number of protons will change and then the symbol will be different. So let me go ahead and show this process to you step by step so it makes more sense. Okay. Starting with what I showed you over here. Nitrogen is in group 5, but it has an atomic number of 7. So let me pull this up so you can see. Nitrogen right here has an atomic number of 7. I get the number from up here. Remember the group number. We got 1, we got 2, we got 3, we got 4, we got 5, 6, 7, 8. Nitrogen is right here. And when it comes to gaining electrons, nitrogen being a nonmetal will gain 3 electrons. How do I know it's 3? Nitrogen's goal is to become like neon, the group 8 element. So nitrogen is trying to become isoelectronic with neon. For it to do that, how many electrons must it gain to be at 10 electrons? You can see right here, it has to gain 1, 2, 3 electrons. So nitrogen has to gain 3 electrons. So right here, I think, I'm trying to remember the picture. What they had is number of protons was equal to 7, and this is positive. I think that's what they had. Number of electrons was 7, and this was negative. So nitrogen gains 3 electrons, and the number of protons remain as positive 7, but number of electron changes to negative 10 because it gained 3 electrons only, not 3 protons also. Oops, let me pull this up like that so you can see the transformation. Let me move this down so it's consistent with the part that's changing. Only number of electrons change. So electrons start at negative 10, 3 again, now we are negative 7, 3 again, now we're at negative 10. Number of protons don't change. So if you look at the overall charge here, the overall charge, so I'll call this overall charge, is 0 for this formula. Once nitrogen gains 3 electrons, overall charge, take this top part, add to the bottom part, we end up with what? Negative 3. For that, the symbol becomes N, negative 3, and the number of electrons is 10. Okay? And this is what we call the nitrogen ion. Normally, we don't usually include this one here. This part is implied, but this is what is nitrogen ion versus on the left, we have nitrogen atom. Okay? Now, the table we have up here does have a lot of information when we go from left to right. So I'm trying to recreate this, and there's a lot of details, so I will go over it. Let me see. We talked about the charges of subatomic. We talked about the gained electrons and the changes. So the next part I'm going to be talking about is this part here, which is the dot formula and how that changes our final representation. Okay? So to talk about this part here, let me scroll down and talk about the transformation from the point of view of Lewis. Once again, because I happen to have looked at your homework questions and I realized how they're asked. So we're telling the same story, and the bottom line of the story is nitrogen is gaining 3 electrons, but we're doing so, let me minimize this. We are doing so, hold on, yeah. We're doing so by focusing on the number of dots. So to do Lewis's dots, to explain the same process, remember group number equal number of dots. So nitrogen is in group 5. So I'm going to draw 5 dots. 1, 2, 3, 4, 5. And please notice when you're drawing these dots, it doesn't really matter where you start as long as when you're going across, you're going, top, left, whatever. I mean, I can start from here and then double whichever one I want. But in the end, you want to make sure they're distributed in horizontal and vertical fashion. Okay? Okay. I start with that. And then the question is, how many dots can be gained to get to 8 dots. Remember, the goal is octet. You look at these dots here. Nitrogen currently has 5 dots. I'm going to draw the additional dots in blue. So 1, 2, 3 dots, right? So the before is actually that once the nitrogen gains dots, I'm going to write here, gains 3 electrons. Now what we end up having is the original nitrogen. Let me draw it in red so you can see the difference. After gaining 3 dots, it looks like this, 3 blue dots. It now looks like this, 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 okay? So once again, I'm trying to be consistent. So this, since nitrogen has gained 3 dots, you represent this like 3 minus. You can put the minus in front or after, showing you that this is nitrogen ion. So I'm being deliberate in the process because your homework does require you to interpret this information. Nitrogen atom we have on the left, showing you the dot space and the group number, and then once again 3 electrons, we have the structure right here. And they went through and showed this transformation for nitrogen right here, did the same with oxygen, and so we're going to move on. So I'm going to do one more part, and then that will allow me to move on, which is the configuration. Same process, but using electronic configuration. I know, I feel like I'm beating this story to death. Okay, now we're using electronic configuration to tell the same transformation. Okay, so this part, I just used the number of electrons here to show you what was going on. Second part, I used Lewis dots. Now I'm showing you the same transformation using electronic configuration. So nitrogen by itself has, let me see, 7 electrons. The configuration for that, based on what nitrogen is, for the configuration, you want to follow my eyes. So imagine the helium is next to hydrogen, right? The first 2 electrons are placed here. First 2 electrons occupy 1s, and we place both electrons there, so it becomes 1s, superscript 2. Electron 3 and 4 in nitrogen will occupy this position, sublevel 2s, 2. 2 plus 2 is 4. We have 3 remaining electrons. The 3 remaining electrons, if you count them, electron 5, 6, 7, where 7 matches the location of nitrogen, those will be in this position here. This position is called 2p sublevel. And in 2p sublevel, we will place 3 electrons here. 1, 2, 3. So in the 2p sublevel, we place 3 electrons. This is electronic configuration of nitrogen. Okay? When nitrogen then gains 3 electrons. So it's the same event being communicated to you, 3 different groups of witnesses. That's kind of how I see it. Chemists are notorious of doing that. They're talking about the same thing, but they're represented in so many different ways. So for me to make sense with my life outside of chemistry, it's like an event happened. Now, right now, I go to a lot of meetings, and I have different friends, co-workers that go to meetings. I know the ones that tell you the story of what happened in the meeting in the big picture. Well, you know, the name is discuss who's going to get fired. And I'm like, what? Well, who's going to get fired? You know, faculty or staff. Blah, blah, blah. Who? Anybody I know? You don't know any of them. I'm like, I need to know names. So then I call another friend, and she's like, okay, listen, this is what happened, okay? They said it at 2 o'clock, and they said blah, 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 and this person would give you a play by play and play by play. They'll give you no big picture, but they'll give you a play by play. So what we're doing right now is kind of this, it's not exactly the same, but we're looking at the same transformation from 3 different points of view. One, using electronic configuration. The other one, we're using the dot diagram, right? And the one before that, we were just tracing or tracking the number of atoms and protons. Sorry, not atomic number and the proton number. Okay, so you want to be able to do all three levels. So back to this. Once the nitrogen gains 3 electrons, right? Now the nitrogen has what? 10 electrons. The symbol has changed to 10 and 3 minus. We now have to place 10 electrons though. So where do I start? We start from here like we did. Let me change the color. Can I change the color? Pink. Yeah, we can do pink. We start from here. The first 2 electrons go here. So now it's 1s2. The next 2 go here. 3 and 4 go here. So this is in the 2s level, we place 2 electrons. 2s level, 2 electrons. Then we move over here. In the 2p level, we have to place how many are remaining? We place the first 2, second 2. So out of the 10, we've placed 4, right? We're left with 6. So we need to place 6. 1, 2, 3, 4, 5, 6. Okay. Based on what we're doing, we're going to place the 6 electrons here. So 2p, 6 electrons go there. When you add your superscript, you get 10. So bottom line, when nitrogen gains 3 electrons, it moves 3 spots forward, but now it has the same number of electrons of neon, and it also has the same configuration. I feel like I've said the point so many different ways. You're like, oh my goodness, move on already. But in your homework, remember, you have to show all these. And you can see here how nitrogen is isoelectronic with neon. Because guess what neon's configuration is? Regular neon has the exact same configuration as nitrogen, 2p6, just like that. So when nitrogen has 3 electrons, its configuration matches neon. So that's why they say nitrogen is isoelectronic with neon when it has 3 electrons like that. So nitrogen 3 minus is isoelectronic with neon. Okay? So hopefully that is clear. And the meaning of those terms is clear. So I've gone through the 3 different levels of that. Let's do the same for the metals. That was a non-metal. The metals is this slide here. It is sodium. I guess I can do sodium. I'll do sodium. Sodium right here. So I'll do all 3 levels for sodium. See the first level, the second level, the third level. First level, number of protons and electrons. Second level, Lewis structure. Third level, configuration. Okay? So let me do the same thing for sodium and then we'll move on. Okay. Our metal this time selected is, I'll say sodium. Symbol Na. So starting with number of protons and electrons. Let me grab this up here, sodium. Sodium is right here, 11. So sodium, atomic number 11. Number of protons, plus 11. Number of electrons, minus 11. Total charge, 0, when sodium is neutral. Okay? So let's see. The goal for sodium for all these group A elements is to get to group A. If sodium wants to get to argon, it has to move how many spots? Skip this part here because D block is not involved. Sodium will have to gain 1, 2, 3, 4, 5, 6, 7. Sodium can't gain 7 electrons to be where argon is. So the best thing sodium can do is to lose 1 electron to be where neon is, because neon is actually a lot closer, right? So when the elements are gaining or losing electrons, their goal is to be like group A. And they'll do so with gaining or losing the least number of electrons possible. So sodium will actually prefer to lose the electron to become like neon. And since neon is just 1 spot before it, it will lose 1 electron. So back to this. Sodium then loses 1 electron. When it loses one electron, now it has -10 because one electron got lost, but the number of protons has not changed, it's +11. Number of electrons has changed, it's -10. Add these two and we get a positive charge. So now sodium will be listed as sodium positive, right? And this is, of course, +1, sodium ion, because it lost an electron, right? You can see the process here. Okay, so we've told the story from the point of view of protons and electrons. We're now going to move on and continue the story from the point of view of Lewis's dots. So Lewis dots. In Lewis dots, we have to look at the group number of sodium. Sodium is in group 1. So start with that. Sodium is in group 1. So you can see from right here, being in group 1, it just has 1 dot. Okay. So we know sodium has to lose 1 electron. And when it loses 1 electron, it gets left with 8 electrons. What? How is that possible? Okay. I mean, if you're anything like me, I'm like, how is it possible? Now, what they do here, though, they don't show you the 8 electrons, which they're trying to simplify it for you, right? So let me just take a step back and simplify it for you. Because remember, the outermost electron is 1, but there's also inner electrons. So in reality, the outermost was like this on the outermost energy level. When that got lost, it revealed the energy level below. But since your book doesn't go into that much detail, let me go ahead and erase that and just say, once the 1 electron is lost, sodium becomes positive. Okay? And this is the story from the point of view of the Lewis dots. Remember, with this, sodium has 11 electrons. Now it only has 10 electrons because 1 electron has been lost. Okay? That's fine. Now we're going to tell the story from the configuration. From the configuration point of view, I need to write the configuration for sodium with 11 electrons. So starting from the beginning, let me erase all of these. Wait, how do I erase this? Delete? Oh, it's a different way of deleting. Okay, let me start with the yellow. So sodium, before it loses anything, has the following configuration. We're going to end here, right? Imagine helium is here. The first 2 electrons, 1 and 2, get placed in the 1s level. So 1s level, we place 2 electrons. Electron 3 and 4 get placed in the 2s level. 2s level, 2 electrons. Electron 5 all the way to 10 get placed in the 2p level. 2p, 6 electrons, right? 1, 2, 3, 4, 5, 6. And then the 11th electron gets placed where the sodium is. At 3s level, we only place 1 electron. That's the configuration. You add the superscripts, 2 plus 2 plus 6 plus 1, we get 11. Yep, done. Okay, now what's the configuration after sodium has lost 1 electron? It only has 10 left over. I'm going to use the pink marker so I can tell the difference of the highlighter. Okay, now we only have 10 electrons to place, right? The first 2 go here. So 1 is 2. The second 2 go here. Electron 3 and 4 go here. 2 is 2. Electron 5 all the way to electron 10 go here. 2p6. Well, we said we had 10 electrons, right? That's it. So the configuration of sodium after it lost 1 electron matches neon. When I write the neon configuration that also has 10 electrons, guess what I get? 1s2, 2s2, 2p6. So if you are asked to describe this using proper term, you say sodium ion is isoelectronic with neon. Okay? So even though I spent a lot of time showing you that, I've already gone over this part here, so y'all know about the charges already. And then you can see then the active exercise that says, write the electronic configuration for calcium ion. With what noble gas are its ions isoelectronic? Even though we have the answer here, I'm going to skip over the answer page and go to the next part because I want us to look at the answers. Okay, so it says write the configuration of calcium ion. So calcium, what will the charge on calcium be based on its position and group number? Can you tell? Okay, but positive what? Because calcium is in this group right here, right? It is positive, but what positive? Exactly. So calcium will be positive too. So if calcium was just by itself without being positive too, see the number up here, 20? It will have 20 electrons. But calcium being positive too just means, this means it has lost 2 electrons. So now it's left with what? 18. So the configuration for calcium after it has lost 2 electrons. Oh, there's different kinds of erasers? Ah, I see. You live and you learn, huh? Okay, so I'm going to use the yellow marker first. Now we're going to go with calcium, but after it's lost 2 electrons. So we're not going to go all the way to this part here. Come on, go back. No, so after it loses 2 electrons, now it only has 18 electrons. That's that position there. So we'll go from the beginning, from here to here. Electron 1 and 2 is going to be 1s2. Electron 3 and 4, 2s. And we place 2 electrons. Oops, yeah, 2 electrons there. Electron 5 all the way to electron 10 will be in the 2p level. And we place 6 there. Electron 11 and 12 will be placed in 3s. We're going to argon, right? 2 away from calcium. Electron 13 all the way to 18 will be placed in 3p. 3p6. Okay? So the configuration for calcium after it loses 2 electrons, now it only has 18 electrons, is 1s2, 2s2, 2p6, 3s2, 3p6. But they wanted to know what this configuration was isoelectronic with. Okay? What do they say here? With what noble gas are its ions isoelectronic? Okay. We already got the calcium configuration ion. Add up all the electrons. 2 plus 2 plus 6. This is 10. And then this is 18. So just find the noble gas element, which is group 8 element that has 18 electrons. That will be argon. So we'll say isoelectronic with argon because it has 18 electrons. Okay? So now that we're done with that, we're good. So let me put this aside over here, then we'll continue. Okay, so now we talk about ionic bonds. We saw that cation and ion crisscross each other, we get ionic bonds. Ionic bonds are strong electrostatic forces, force of attraction that hold ions in a fixed position in the crystal. So we have cations that are positive, attracting anions in a bond. And then we're being told here, nearly all ionic compounds are solid at room temperatures. Usually with this, when I'm reading such, to me, abstract information, I like to find an anchor based on something I know. Okay? Sodium chloride is an example, is one of those poster child examples of ionic bonds. Sodium chloride is table salt. We tend to see table salt as a solid. So we're being told here ionic bonds are usually solids. Okay, ionic bonds, table salts are usually solid. I've rarely ever seen table salt that's a liquid. People say soy sauce is literally salt, and I'm like, there's other stuff in there. There's liquid, there's brown stuff. So it's more than just salt, even though it is very salty. So in ionic bonds, cations and anions are in an ionic compound are always in such number there the compound is electrically neutral. Translation: in a compound, the cation charge is neutralized by anion charge. So you want to use as many cations as anions to make sure the whole compound is neutral, because compounds are never have a charge. If they have a charge, they're an ion. Okay? We talked about this part before. Ionic crystals are very strong, which is why nearly all ionic compounds are solids at room temperature. Liquid ionic compounds and water solution of ionic compounds are good conductors of electricity. We'll discuss that later on. Look at that, table salt. So they're showing you here what happens to sodium. The same thing we discussed, right? Sodium lost 1 electron. See, the number of electrons here changes as after it loses 1 to become sodium ion. Chlorine goes from 17 electrons to 18 electrons. It gained that 1 electron, right? Goes from neutral atom to negative ion. Once they form opposite charges, they attract each other. Attract, opposites attract. Okay? And they combine to form sodium chloride, which we know as table salt. Just sitting here thinking about this, even though I just ate, it's making me think about food. Now, if you somehow manage to melt, I don't know why you will be doing this. Okay? I don't know why. But if you happen to melt salt, it will actually conduct electricity. You can see here, this is a conductivity apparatus, conductivity. And you can see how the melted salt is actually conducting electricity, because you can see the light in this bulb. Okay? Okay, after seeing all that, we're now going to be looking at covalent bonds. So let me check real quick, because I know what's in your homework. Okay, what they failed to do here, let me go ahead and do that, because I do have it as a list of things before we go into covalent bonds, is to use Lewis dot structures to form ionic bonds. So, because I know it's in your homework, using Lewis dot structures to form ionic compounds. Okay? Summary. Number of dots equal group number. So let's start with a simple one. What if we're trying to find a compound between calcium and chlorine? Okay, so let's grab this from down here. What group is calcium in? Calcium is in group 2. So I'm going to draw calcium on the left with 2 dots. And remember, this is our metal. And on the right, I'm going to draw our non-metal. Non-metal. Our non-metal. This is chlorine. So our non-metal is chlorine right here. And chlorine is in group 7. So I'm going to draw chlorine. I'm going to draw 7 dots. 1, 2, 3, 4, 5, 6, 7. Okay. So looking at, you know that metals lose, right? And then non-metals gain. This is our clue here. How many dots is chlorine away from getting to 8? So even though we haven't discussed the octet rule, the rule of 8 officially, we're still displaying it over and over again. Chlorine is trying to make sure the outer layer, the energy layer, has 8 electrons. Right now it has 7. So what must chlorine do to get to 8? What's the easiest way or the quickest way for chlorine to get to 8? It has 7 electrons in the outermost layer of energy. Can you see that? Okay, chlorine has to gain an electron. Okay, the electron has to come from somewhere, right? So what happens is chlorine gains the electron from calcium. And so let me draw the electron differently over here. Now Lewis usually draws them as dots, but when I was in high school and stuff, the teachers took liberties. But so calcium will lose its one electron to chlorine. Okay, so in the end, calcium has to lose both electrons. So guess what? Another chlorine gets brought in. 1, 2, 3, 4, 5, 6, 7. Same thing happens. This goes over here. So in the end, what we're left with after calcium loses both electrons is now C8 plus, but then the chlorines are now Cl dot 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 dot, and we end up with two of these chlorines with a negative charge. Okay, we end up with two of them with a negative charge. And so this is like saying you have two positives here, then you have two negatives here. It's kind of like that. So in the end, we end up with a neutral compound because these neutralize each other. So you end up with a neutral compound, neutral. So if you're asked from the point of view of, what's his name, Lewis, to explain what's going on, this is how you explain it. The calcium combines with two chloride ions to get a compound. How do you know that? You can see that right here, right? So in the end, the ionic formula we get is calcium and two chlorines like that. Okay? Let me do that again for an interesting one, then we'll go to covalent compounds. Let's do magnesium and nitrogen. Once again, magnesium is going to be your cation. It's going to be your metal. Nitrogen will be your anion. Okay. Magnesium is right here, group 2, right? So magnesium has got 2 dots. The nitrogen on top is right here, group 5. 1, 2, 3, 4, 5. Okay. Let's start with the needs of the nonmetal. The nonmetal currently only has 5 dots. It's closest to neon, so it just needs 3 dots to advance over here, right? So this is going to gain 3 electrons. What is it gaining from? The only giver that's available is magnesium. This one magnesium is not sufficient to fulfill the needs of nitrogen, right? So the rule is bring in another magnesium. Thank you. Because the final compound has to be neutral. Okay, so this magnesium and then the next magnesium are going to together help this nitrogen. So this comes here, this comes here, this comes here. Okay? And then, well, this magnesium only got to give its 1 electron, so we got to give the other electron. So bring the other nitrogen. Nitrogen comes here. 1, 2, 3, 4, 5, right? So this magnesium gives to that nitrogen. But look, we got more room. So bring in another magnesium right here. As I said, we do an interesting one. So finally, we got this over here. We got this over here. Is everybody satisfied? Yeah. Have the nitrogens gained 3 electrons? Yes. Right here. Gain 3 electrons. So what happens is magnesium gains 3 electrons, but magnesium gives out 2 electrons, right? So you see here, each magnesium is losing 2 electrons. Each nitrogen is gaining 3 electrons. This one here loses 2 electrons. This one here loses 2 electrons. This one here loses 2 electrons. But it takes 3 magnesiums to satisfy 2 nitrogen. So in the end, when we're done with this, we consolidate, right? 1, 2, 3 magnesium. It took 3 magnesiums to each gain a charge of +2. And then as the 3 magnesium lost their 2 electrons, it took 2 nitrogens to become like this in order to have the sufficient charge. Each one gained 3, right? So it's like this. The 3 magnesium combined with 2 nitrogen, then we get our compound, magnesium. So as far as the charge is concerned, it would be like this. Magnesium 3, nitrogen 2, okay? And I'm trying to look back and see how I wrote this one here. Yeah, this one ends like this. Calcium chloride, magnesium 3. It takes 3 magnesiums and 2 nitrogens to form the compound. Okay. The other way you can work it out as you guys are working your problems out, magnesium forms a charge of +2. Nitrogen forms a charge of -3. You can crisscross this. Magnesium becomes like this, -2. Nitrogen +3. The charges drop off and we end up with magnesium 3, nitrogen 2. But this is the desired answer. This is the process. So some of the questions in the homework ask for process. This will help you get to the process, okay? Okay, so how does this make sense? Since they have different charges. Remember, it takes 3 magnesium. Each magnesium has a charge of +2, +2, +2, right? So we end up with a charge of +6. And it takes 2 nitrogen. Each nitrogen will have a charge of -3. So we'll have a charge of -6 total, +6 total, and these neutralize each other, and they create a neutral compound. By the way, I don't remember if I told you guys this, but when you're going over the video at home, feel free to rewind. I have one student who told me she has to rewind 3 or 4 times sometimes to really get it. That's what I do with Netflix. When I'm watching a movie and it involves some kind of mystery and it's complex, or even if there's an accent or something and I know I have an accent, rewind it as long as you need to understand. Don't just watch it one time. Feel free to rewind because you're taking notes and making sure you understand it. So you have the liberty of rewinding. It's gotten so bad with me, I'm not even ashamed of admitting this. When I'm watching TV, I forget it's not Netflix, and I'm watching the news and something has happened, like, oh my goodness, rewinding. And my husband said, this is not Netflix. I'm like, oh, I'm not gonna watch it on like TV anymore. I'm gonna wait till it's on YouTube. Listen, okay? I am not ashamed. I'm just owning up to the truth. I watch videos that I can rewind to really get the content. So I'm just advising you guys do the same. Right, do it, rewind to learn this stuff. Okay? So I'm like, my friend gets angry at me. Why don't you watch news? Because I'm like, because I can't rewind. And she's like, I don't even know why I talk to you. To each his own, to each his own. Okay, so now that we've done ionic bonds, now I'm going to show you guys how to use covalent bonds, okay? So with the covalent bonds, now once again, this topic is not very long. We're kind of almost more than halfway through the slides, but the process itself is kind of long as we're working on this part. In covalent bonds, what I want to do this time is actually show you the process, and then I'll go ahead and define. With covalent bonds, nonmetals are combining with each other to form a bond. So it's 2 nonmetals, nonmetal and metal. Chemical bonds form between 2 or more atoms that share 1 or more pair of electrons. So here, with the sharing, they can share 1, 2, or 3 electrons. Kind of like the other part with the transfer, okay? With the molecular compounds, when hydrogen fluoride and methane are condensed into liquids, they are non-conductors, like water. These are called molecular compounds. So we saw that ionic compounds conduct electricity. Molecular compounds, though, don't. The ultimate structural unit for individual particle of a molecular compound is called a molecule. And they show you here the difference. So what I want to do real quick before I go into all the details in the dialogue, I want to do a compare-contrast real quick. Okay, so we're comparing ionic compounds. So this is kind of like a remix, right? Ionic compounds, and then we have molecular compounds, We're going to look at what's similar about them, what's different. Okay, based on the little we've learned so far. Ionic compounds from metal and non-metal most of the time. Molecular compounds, non-metal and, oops, I'm trying to be consistent, non-metal. Okay, metal, non-metal, non-metal, non-metal. Okay, here forms ions. I'll say here doesn't form ions. Okay, so this is like 1 and number 2. Number 3, metals lose electrons, non-metals gain electrons. And one thing I learned when I get very distracted, my coworkers have said some stuff about me that I shall not repeat that involves me being distracted. And so it does help me to write things down. Okay. And sometimes the more distracted I am, the more I write down because it does help me to focus my mind. Okay. So let's see. Metals lose electrons, non-metals gain electrons. Here, there's no metals and non-metals, so non-metals share electrons to form bonds. So here, purpose, of course, to form bonds. What else? Now they're saying ultimately when the structure is formed, mostly solid, made up of repeating units. They didn't say this earlier, but yeah, the reality is when you look at a table salt crystal, it's a solid made up of a bunch of repeating units. This one here, mostly liquid and gas, made up of individual units. So just in case it ever comes up, that. But I'll say the first 3 are the key differences, right? You know that another key difference here is how they form the bond, sharing versus losing and gaining, which is sometimes called transfer. So sometimes the one term word for this one here is the transfer electrons versus sharing electrons, okay? Then here, of course, you have metals and non-metals, here non-metal, non-metal. Okay, so I'm trying to make sure I've covered everything. Okay, before I start forming bonds here, which I think that will be my focus for today, forming bonds, I want to go ahead and use, I'll say here, using Lewis structure to determine number of covalent bonds formed. Okay, so it appears I'm going off script, and I am, because I looked at your homework and sometimes there's a disconnect between the lecture and the homework. I'm trying to make sure that you have sufficient skills to approach the homework. Okay, so we're going to use Lewis structure to determine the number of covalent bonds formed. To make this go easier, I'm actually going to use period 2. Period 2 is this group right here. Let me see if I can make this small so I can bring it here. Oh, let me make this smaller. Oh, there. Okay, so hopefully you can see this. Period 2 is this right here, from lithium, beryllium, all the way to fluorine. So let me go ahead and erase this. So we'll use Lewis structure or Lewis symbols or structure to determine the number of covalent bonds formed. Now, I'm going to list the metals: lithium, beryllium, boron. For the most part, these form, boron is a nonmetal. These form ionic bonds but it still works. Okay, if you look at lithium, lithium is in group 1. So lithium just has 1 dot. Guess what? It forms 1 bond. If you look at beryllium, let me write this differently. Lewis structure, and then I write here bonds. Okay, so lithium is usually in group 1. Number of bonds for lithium is 1 bond, like that. Okay, I'm kind of developing this as I'm going. I'm literally making it up on the go. So I'll say here group number. So lithium is in group 1. It has 1 electron dot, and then there, number of bonds, 1. Okay, you can call it Lewis structure or Lewis symbol. Okay, based on that logic, look at group 2. I have here beryllium. Beryllium has the 2 dots. Guess how many bonds it has? Be, like that. Okay, boron is in group 3. Boron is surrounded by how many dots, being in group 3 according to Lewis structure? 3 dots. Guess how many bonds boron has? 3 bonds. So when we're seeing boron in bonds, bonding with other elements, this is the normal bonds. So I need to emphasize the normal bonding structure. Of course, with every rule in chemistry, there is that exception. Okay. Okay, so having seen group 1, group 2, group 3, it's almost safe to say that there is a correlation here, right? Before I continue, the correlation here number of unpaired dots. The dots are technically electrons, so I should say electrons. I know better. Electrons equal number of bonds, right? So you can see here, these are the unpaired electrons. These are the unpaired electrons. These are the unpaired electrons. So number of unpaired electrons equal number of bonds. That's really the rule. Okay, so what happens when we get to group 4? We continue, right? This is kind of the summary we're making, the observation we're making. Let's see if the observation continues. Group number 4, carbon, 4 dots, 1, 2, 3, 4. Number of bonds carbon normally forms, 1, 2, 3, 4. Aha! It continues. Number 5, group number 5. So I've done lithium, I've done beryllium, I've gone over to boron, I've done carbon. Let's see if this continues. Now I'm moving over to nitrogen, group 5. Nitrogen. Okay, let's see how the dots look different this time. 1, 2, 3, 4, 5. Number of unpaired electrons equal number of bonds. I only have 3 unpaired electrons now. Okay, so I'm going to look at this, leave the dots, make the unpaired electron bonds. This is a normal bonding pattern for nitrogen. Ah, see the trend in chemistry? Okay, now I'm moving on to up here, oxygen. Oxygen has how many dots? 1, 2, 3, 4, 5, 6. Oxygen, normal bonding pattern, 2 dots, 2 dots. These unpaired dots become bonds. So we continue. So it does help a lot when it comes to drawing, what's it called? Covalent compounds, right? And then our final one that we're working on is fluorine. Fluorine has 1, 2, 3, 4, 5, 6, 7. So fluorine, when it forms a bond, normally has 1, 2, 3, 4, 5, 6, 7. Yeah. Okay. So as we have looked at this, now we're looking at the summary. You can see, again, we are low-key talking about the octet rule. At some point, we will learn this, and I want to mention this right now. Okay? At some point, we will learn that one bond, every bond we draw, is composed of 2 electrons. So as we're going through and looking at the bonding pattern with carbon, we see there are 4 bonds that surround it. That's 2 electrons, 2 electrons, 2 electrons, 2 electrons. Nitrogen, 3 bonds, a lone pair, 2 electrons, 2 electrons, 2 electrons, 2 electrons. Oxygen, 2 bonds, 2 sets of lone pairs, 2 electrons, 2 electrons, 2 electrons, 2 electrons. Fluorine, 2 electrons are bonded, the other 3 sets of 2 are lone pairs. So each of these right here, starting with carbon, these, when they form a bond, get to octet. This gets to octet. This gets to octet, which is 8 electrons. Ooh, octet, not octet. Oh, octet. Okay, so starting with carbon, when carbon forms 4 bonds around it, it ends up with 8 electrons. Same thing with nitrogen, 3 bonds, 1 lone pair. Oxygen, 2 bonds, 2 lone pair. See the pattern here? There's so many hidden patterns in chemistry, and for me, that is exciting. I'm like, what's the pattern? What's the trend? You see that from carbon, I call these a SNOF group, C-N-O-F, SNOF. It's not really a thing. They are a group, but don't really have a name. So I made up my own name because I can. Anyway, has it gone global? No, it hasn't even gone viral. So no, nobody really. I just call it SNOF. Carbon, nitrogen, oxygen, fluorine, because they do have that trend. Carbon having all 4 groups being single bonds. Nitrogen has 3 single bonds, 1 lone pair. Oxygen, 2 bonds, 2 lone pairs. Fluorine, 1 bond, 3 lone pairs. So you see the pattern here, right? 4 bonds, 0 lone pair. Here we got 3 bonds, 1 lone pair. Here you got 2 bonds, 2 lone pair. And here we got 1 bond, 3 lone pairs. So as the number of lone pair increases, the number of bonds decrease. But in the end, you end up with 4 total, 4 total, 4 total, 4 total. Okay? So hopefully you're seeing a trend here. And as we draw our Lewis structures, we'll go from there. So let me show the Lewis structure. Once again, I'll show one, and then when we come back, which is, yeah, what we're talking about right here, the Lewis diagram. When we come back on Thursday, we'll continue this. So let me show one Lewis structure here using the elements that they have, hydrogen. So we're drawing the covalent bond between 2 hydrogens. So each hydrogen has, because they're both in group 1, so this hydrogen is in group 1. Look right here. The hydrogen is in group 1, right? So each one has 1 dot according to Lewis, and they share electrons, share unpaired electrons. So when they do that, they both end up like this, H, like that, and then that shared electron pair becomes a bond. And this is how covalent bond is formed, and it's showing you the formula as H2. Okay? Let me do the same thing, one more thing, and then I'll be done for today, because I think we're more than halfway through. To draw the covalent bond between carbon and hydrogen. Okay. So remember, carbon is in group 4, right? Because carbon is right here. The group number is labeled above, so it's in group 4. That's 4 dots. 1, 2, 3, 4. And then we got, what is it? Hydrogen is in group 1 plus hydrogen in group 1. So let me use a different color for hydrogen. Hydrogen will be let's go with red because it's bright. Hydrogen is in group 1. Okay. Carbon needs 4 electrons to get to octet, right? So in this case here, we would the goal is covalent bond, and we achieve covalent bond by sharing electrons. We have to remember that. So how do they share? Let's start with the carbon in the middle, draw our 4 dots around it, then bring in the hydrogen. The one hydrogen will share right here, and now the carbon has 5. Bring in another hydrogen. The carbon now has 6 electrons. Bring in another hydrogen. Carbon has 7 electrons. Bring in the final hydrogen. Carbon has 8. So now we have carbon forming 4 bonds with each hydrogen. Well, forming 4 bonds total, and then we need 4 hydrogens. So this formula is going to be CH4. It takes 4 hydrogens to help the carbon get to an octet. Okay, and so we'll approach this again from a different point of view when we get to the others. I just wanted to go over this so you can see the similarity and differences between the ionic. In the ionic, someone was losing, someone was gaining, right? In the covalent, though, there is sharing, but once again, the goal is to get to those 8 electrons. Okay, this is where I'm going to stop today. We'll finish the rest of this chapter on Thursday. Any questions? And I hope to remember this configuration. So I didn't take a picture of it because usually in my other slides, oh my goodness, there was one time I'm like, where is it? Where's the piece of paper? Where has it gone? Yeah, it's like I struggle to get an orientation when I'm not moving stuff around. But I think this works. I hope you guys can see this at home because my computer screen is large, but I think this will work. Let me take a screenshot of it. Oh, I see it's not working. It's not working because I need the other screen of this. Okay, my phone is charging somewhere, y'all. It's a struggle. Let me find my phone. Take a screenshot of this so I don't forget. I'm trying to use my iPad. I'm trying to use my iPad. Okay, this works a lot better. Let me take a screenshot of this so I can remember the configuration I use. I shouldn't forget since I've actually gotten it here, but okay. This is all I have for today. If you don't have any other questions, I guess I'll see you on Thursday. Okay. Let me X out of here.